Sure. Okay, so as I said, this is a summary of the stuff we have going on. I'll work on this stuff to make sure we get your grades figured out. What I'm going to do is I'm going to be keeping the official grade book in Blackboard so that you will actually have an updated grade. And what I'll probably do is I will probably enter all of Unit 1's homework as a single grade when I transfer it over to Blackboard instead of entering it as individual assignments, just to make it a little bit easier on myself. And so what it'll probably be is your Unit 1, it'll probably go in as Unit 1 test will be 100 points. Unit 1 homework then is going to be 200 points. And then from there, we'll just pick up. I don't have, in-class activities I won't be able to grade for Unit 1. Unit 2 then will be kind of the same way. It'll be homework. It'll be worth 200 points for Unit 2. In-class activities will be worth 100 points. And we won't grade on that if like you had an excuse to be gone last week with an emergency. That won't count against you. As long as you're here a majority of the time and not like significantly gone, that won't be a problem there. Then of course the Unit 2 test will be 100 points. I'm looking at right now, probably doing, today is the 30th, probably finishing up M5, maybe starting M6. On the 1st, we'll make sure we finish up M6, possibly start M7, excuse me. On the 6th, it'll be M7 all the way. On the 8th, wow, I'm off today. On the 8th, we'll get M8 done. And like I said, we're a little bit ahead of this schedule. So on the 8th, we might take some time to go back and look through M1 and M2 to make sure you have those turned in. That way I'll have all the homework from Unit 2, the Unit M, basically, I should call it. I'll have all that so that I can grade it and get a homework grade put in the books for you. Then probably looking at either November 13th or November 15th, one of those 2 dates, is going to be our Unit 2 test in class. Come on now. Probably looking more towards November 13th for being Unit 2 test, just so you guys are aware. And then that gives us about 6 weeks then to cover Unit 3, which is our statistics. Well, not really statistics, more data analysis. So that should put us at a good pace right there. And like I said, if we have to go back to November 15th, I'm not worried. We do have an extra day or two in there to work on stuff. I just want to make sure everybody feels a little bit more organized moving forward. I know things maybe haven't been that way so far, so I want to make sure everybody's feeling good about stuff. Okay, so last class, we left off, we were talking about, we were in Unit M5, and we had talked about these models. And just kind of wrap up a little bit of M4 and get us back into M5. We had different types of models we were looking at. The one that we had looked at in M4 was called a linear model. So let's take a look at some examples here. And first I want to determine if these are linear models or nonlinear models. So for example, say Pat has $1,200 in, we're just going to say in a piggy bank. so that we don't have to worry about interest. Pat adds $50 every month. I want to model the amount in the piggy bank. First of all, would this be a linear model or a nonlinear model? Linear. What is one of the biggest attributes about a linear model? There we go. We have a constant rate of change. And here, of course, that rate of change is what? $50. There's a second part to it. Every month. Yeah. And so that rate of change, anytime there's a rate, there's two values that are involved in it. It's a fraction. There's a numerator and a denominator. This would be written as $50 per month. Kind of like a great rate of change, a classic example of rate of change is speed. Speed, you're used to speed being, 55 miles per hour. When you see that, what it really means is 55 miles in 1 hour. A rate really is a comparison between two numbers. And when we're talking about rates of change, which is basically the slope on a linear graph, it really is those two numbers. If you were to graph this, in fact, I want you to take just a couple of minutes and just sketch a quick little graph of what the balance of this piggy bank would be, starting at month 0, and then just go for 6 months. So I'll let you guys have a couple minutes to just sketch that graph quick, and we'll talk about it here in just a minute or two. May not be totally done with the sketch yet, but that's okay. Looking at this graph, above 0 on month 0, what would be the balance in the piggy bank? 1,200, yep. Then at the end of month 1, that would go up to 1,250. There we go. The end of month 2, it would be 1,303, 1,350. The end of month 4, end of month 5, 50, and end of month 6, 1,500. I didn't do my dots real well there, but there we go. You guys will find there's a good reason why I'm an art teacher, or not an art teacher, I'm a math teacher. My drawing really is horrible. Two things I want to point out here, though. One is, this is called a linear model because what shape does it make on the graph? It makes a line on the graph, exactly. So a linear model is named off of its appearance on the graph. The second is the graph has two distinct parts. For those of you that had formal algebra in high school, when you graphed lines, you talked about two very important parts of the lines. You had y equals, they usually say mx plus b. I often will write it as y equals b plus mx. Where this is that starting point here, the y-intercept, exactly. And that y-intercept is called the y-intercept because that's where it crosses that y-axis. It's also what we call an initial condition. Not that you need to know that big word, but what it means is that's where when x equals 0, or a lot of times across the bottom it's not x, it's t, or t equals 0. So that's the starting point of this graph. Everything starts from there and builds from there. Then, of course, that part that's multiplying x is called what? The m is called the slope. And that slope is that rate of change that we discussed. So to create a linear model for this graph, this situation, like I said, it makes more sense for me to use this version, but either one of them is fine. It's going to be y equals, what is the starting point of our graph up here? 1200 plus, for every period of time, how much does it go up? The rate of change would be, it goes up how much each month? $50 per month. Now, it doesn't matter, we put X or T or whatever in there. Now, we should specify that X equals the number of months. Because if X didn't equal months, then we'd have to adjust that rate of change. That is $50 per month. You know, if X were years, we'd have to adjust that then as $600 a year instead of $50 per month. Then, of course, we should specify that Y is the balance. And one of the things I like about this curriculum, these materials, is they're not stuck on using X and Y. They might put M in for the month and B in for the balance so that the letters actually do have meaning. One thing you'll notice, we said that rate of change was $50 per month. If we look at this graph up here, what do these numbers on our horizontal axis, I believe this material calls it the predictor axis. What do those numbers represent? Months, very good. And these numbers going up, the y-axis, the dependent axis, or the reactionary axis, what do those numbers represent? Dollars. And notice our rate of change was dollars per month. And the rate of change will always be like that. The numerator will always be the unit on that vertical axis. And the denominator is always going to be the unit on the horizontal axis. And so then this number is going to be a horizontal change. This number will be a vertical change. So if we had one of those linear models, so let's look at this here. I'm going to start out. We're going to pretend this looks like a straight line. Actually, I didn't do too bad there. So looking at this, First, let's write the equation for it. What is the starting value here? Yep. So what value is that for this line? The number, yep. That would be 700. Very good. Now, is this line going up or down? Down. It is what we call decreasing. So it's going to be perfect, a negative slope or a negative rate of change. We're getting smaller as we change. So now usually when we write that slope or rate of change, remember it's vertical change over horizontal change. I guess I wrote those small enough you can't really read them, but horizontal change, we try to make this equal to 1 unit if we can. Well, we have months down here, so let's go 1 month. That would be 1 month. So the horizontal change here, if we draw this in, this is 1 month. We often forget about putting the units in here, but they are actually pretty important to us. What is our vertical change here? $200. Good. And it's going down. Technically, it's a negative $200, but we already have the negative sign in over here. So the change was a negative $200 in 1 month. So whether we use X or T or whatever, if we use time, T for time or M for months, or X just because it's horizontal, doesn't matter. It's minus $200 times, let's use T for time because it's a little bit more appropriate. We've created that linear model. And we did. If we were asked just to find the slope or rate of change, this is the part we'd be looking for, negative $200 per month. Well, we looked at some examples last time where it didn't work out quite that cleanly. We had examples where it added a certain amount every time. So we're going to keep the numbers a little bit simple here. Let's say we start with, I'm going to start with $10,000 just to make the first couple of calculations a little easier. The balance increases 4% each year. So what I want you to do for me here, we did this a little bit last time. I want you guys to work on year, and we're going to start out just year 0. The balance is $10,000. So find the balance at the end of each year. Let's have you go for for 8 years. Now remember, we did find a shortcut for finding this balance. We could find 4%. Adding 4%, there were 2 ways we could do it. We could take the $10,000 times 0.04, which gave us $400. And then we could add that together. Give us $10,400. But rather than finding that 4% and adding it on, we found a shortcut. The $400 is 4%. The $10,000 is what percent? Well, that's the whole thing, isn't it? That was the starting amount. That's 100%. So what percent did we end up with at the end of the year? Well, 100 plus 4 is 104%. So what we found was to find that end of the year balance, rather than doing times 0.04 and having to add it back on, we could just do 10,000 times 104% as a decimal is 1.04. And it gave us that 10,400 directly. So I'm going to have you guys using that, fill in that table quick, up to about 8 years. And if you have if you're done before I start talking again, we'll have you start sketching a graph of it. I'll give you a couple minutes to work on it. I'll give you about 3 or 4 minutes to work. Let's see how you're doing so far. I realize this takes a while to get these figured out. I'm going to cheat because I can. And I'm going to use a spreadsheet. For you guys, by the way, if you're doing your out-of-class activities and you want to use Excel to do it, that is just fine. If you're doing them as a Word document and printing them off and sending them that way, it's real easy. I'm going to do a different Word document here. In the middle of a Word document, if you're typing along, and you want to put in an Excel spreadsheet, you're typing in your answers, if you go to Insert, Tables, if you go down here, it says Excel spreadsheet, it'll actually put a small spreadsheet right in there for you. And if you make the window bigger or smaller here, it'll increase the number of cells it puts in it for you. And once you click out of it, it just goes back. It looks like a regular table. You double click it and it opens back up in Excel. So you can use that if you want to on your homework. I don't know if it'll allow you to paste that stuff in to the Carnegie website. I know sometimes you can just highlight it and use Control-C to copy it and then paste it. Yep, that's fine. You can just scan it and email it to me and then write a note or something on the assignment that you emailed it separate. Or when you send the email, just make sure you're clear what assignment it goes with. The email address, by the way, there's 2 of them. Either one will work. It's either todd.hoff@witc.edu, or you can send it to thoff@nicoletcollege.edu. The top one's usually a little bit easier to remember, but if you go to Blackboard and click, you should be able to click on course tools and go to email instructor, and it'll send it to me there as well. Okay, so looking at this, we wanted to add 4%. So what was the balance at the end of the first year? 10,400. Now in Excel, the way I would do it is I just put equals. I'd click on the balance above it and then times, which is the asterisk, 1.04. Perfect. That's that 104%. And now because I did it that way, I can just fill this down and it'll do that calculation over and over again. So at the end of year 8, did you guys come up with $13,685.69? Perfect. Now I don't know how much time you had to graph it, so we're going to do that right now. So there is our, oops, I'm going to adjust my axis a little bit here. Format axis, there we go. Our minimum number, 9,500 should be fine. There we go. So that gives us our graph there. Now this graph, because it's small, it's a little bit hard to see how things work. So what I'm going to do is I'm just going to reformat it a little bit to make it a little clearer to see the shape of the line. And because I can't get it all on the screen, unfortunately, it's a little tough. It almost looks linear, but if I try to draw a line through it, we'll see that it doesn't quite fit. Oh, this ain't gonna let me do a line, is it? Well, let's do this. We'll cheat. So there's our graph. So now I can draw a line on it. And for you guys on paper, you'd be taking a piece of paper or a ruler or whatever. And I notice those points don't quite fall on that line. So this is not a linear model. In fact, if I keep going up here, if it were a linear model, it would increase by the same amount every time. And when we looked at our table here, we noticed that first year it went up by $400. The second year it went up by a little bit more, didn't it? It increased by, oops. So it went up $400 that first year. The second year it went up by how much? $416. And the third year, a little bit more. So it's obviously not a linear model. It's increasing by considerably more each year. Now I want to take a look at then something that goes the opposite effect. So what we're going to have is we're going to have this next example. Sam has saved $10,000. Sam is going to withdraw 15% each year. So we're going to do the same type of thing. We're going to create a table starting at year 0 with a balance of $10,000. And we're going to use a shortcut again. Now, what we could do here is we could take that $10,000 times, what are we going to use for 15%? 0.15, perfect, which would be $1,500. And then we could take 10,000 minus 1,500 would get us $8,500. Go for it. Tell me what to do. Yep, perfect. Yeah, because we had the full amount, the 100%. The 1,500 was 15%, so our ending balance was 85%. So yeah, all we would have to do is start out with the $10,000, and instead of multiplying by 15% and subtracting it, we can just multiply by 0.85 or 85% to get that ending balance. Yes, you can assume they won't be linear. And yes, and you can assume you can always use this. It's either going to be 100% minus the percent decrease in this case, or plus the percent increase to get what your ending percent would be. So I'm going to have you go ahead and fill that in again up to year, oh no, let's just go up to year 7 for this one. And if you get time to sketch a little graph, go ahead to do that. Okay, so let's see how you're doing so far. So our model here again is each year that balance is multiplied by 0.85. So at the end of the first year, we're from 10,000 down to 8,500. What's the balance at the end of year 2? Yep, you're right, 7225, perfect. How about the end of year 7? Perfect, 3,205.77. And if we were to graph this again, there's our picture of our graph. And if we drew a line in there, we would still again see that this is not, here's my line. This is not linear because all those points fall below the line. It makes that curve. Now, we did get to the point last class where we talked a little bit about the general equation. If I just wanted to find year 7 and not want to have to find every year in between here, what we've been doing so far is called a recursive model. What a recursive model is we find the current value from the previous value. So if we wanted to know year 7, we had to know year 6. We would use year 6 to find year 7. But what if I didn't want to go through every year recursively like that? What if I just wanted to jump from year 0 to year 7? Well, every year, what did we multiply by here to get to the next year? Yep, 85%, 0.85. So to get to year 7, we'd have to multiply by that how many times? 7 times. In math, we have a mechanism for multiplying by the same number over and over again, and that is a power. Exactly. So we could have done the 10,000 times 0.85 to the power of 7. And we get that 3,205.77. Like this? Okay. Let me go through that in just a second. That's okay. That's a very good question. So right here, this formula, because it has this piece of the formula is called an exponent. An exponent has 2 parts. It has the base and it has the power. So for this exponent, the base is the 0.85 and the power is the 7. That is why this is called an exponential model. In an exponential model, now this fits you, put me right up to your question there. There are 2 types. This is kind of where we ended last Wednesday. The first type is exponential growth. Exponential growth was where up above we had 100% plus. We used 4% in that problem, so we got 104%. So our model for exponential growth follows that. The balance, I'm just going to use the variable y for balance, is equal to an initial value. Now, the math symbol that's usually used, y is the current balance. Y with a little 0 there is called the initial balance. You can think of it as the technical pronunciation is y naught or y0, either one works. That is the value at year 0 or at time 0. Times For exponential growth, it's 1 plus our rate to the power of x or t or whatever you want to put up there. Now let's look at this here. This is this right here. Where does that 1 come from? It's the 100%. That means the rate r must be our percent as a decimal. There you go. So for this formula, we started out with $10,000 times, it would be 1 plus 0.04. If we wanted to go year 7 or 8 or whatever, the year would be X. So the balance at the end of a certain year, Y, is equal to that initial amount, the 10,000, times 1 plus 0.04 to the power of X, which is our year that we're looking at. Any questions on that? Okay. So then we had exponential decay as the next piece. And exponential decay is kind of like what we just did. We had the 100% and we subtracted 15% to get that every year the ending balance was 85%. So the formula we used, the ending balance is equal to, or the balance at a specific year is equal to the starting balance times 1 minus r to the power of x. So now again, this is just this here. It's 1 minus r because we're decreasing. So for the model we just did, we started at $10,000. So that initial amount was 10,000 times 1 minus 15% was 0.15 to the power of x. If I give you a model, let's say I give you y equals 7,200 times 0.6 to the power of x. Two questions. One is, what is the value at the beginning? So at time equals 0, what's the value? 7,200, very good. That's very much similar to the y-intercept in the linear models, that starting value. Second question, is this growth or decay? Perfect. This value is less than 1, so it is decay. Obviously, to get to that value of 0.6, it had to be 1 minus something to get us to 0.6. So it is actually, and what is our rate of decay can be found. What number would we be subtracting from 1 to get to 0.6? Point 0.6, you're thinking 0.06. 0.4, there you go. So yes, it would be 40% per period. We didn't really specify whether X was years or months or days or whatever. But yeah, whatever period is represented by X, it's decaying 40% per period. So for this one, what is our starting amount? You got it. We're starting at 250. Growth or decay? Growth. Good. Because this is bigger than 1. And of course, what is the rate of growth? You had it. 9%. Because it had to be 100 plus 9 to get 1.09. Perfect. Okay, so now kind of jumping back into our packet, our materials here then, I want to look at what are some other types of situations. Between the two of you, you can discuss this a little bit quick and we'll talk about it in a few minutes. Do you guys need a break at all? Sure, let's do that. Let's take 10 minutes. It's 11:36. Normally I do try to take a break in a 2-hour class. So it's 11:36. Let's come back at 11:45. What other things that you think they might not necessarily be so, but we'll talk about it as a group here in a little bit. What type of things do you think might represent or might be best represented by exponential growth and by exponential decay? And just see if you can come up with a couple examples. So you technically have a few minutes left on your break, so we'll let you have your few minutes and we'll talk about these in just a few. Take a look. So we came up for exponential growth. I heard you say population. And you said weight. I'm not so sure about weight. Weight to age, but we'll put it down there as a possibility. Was there anything else that you can think of for exponential growth? Okay. Interest on an account, any generic account. Of course, yeah, that one, compound interest is the big one. Salary, yeah, actually, if you have like a percent, if like we get a cost of living raise, which is like 0.8% a year, that would be exponential growth. Very slow exponential growth, but it is growth. That's a good one. Basically anything where they take a percent of it and add it on. Cost of living is an exponential growth. You know, it goes up by a certain percent every year. Anything for exponential decay? Like a balance on a loan or something like that. Yep. Sea level? You know, that's actually a very good point. There's a scientific argument there that I don't want to get into. There's arguments as to whether sea level is constantly rising. If you look at historical data over like 10,000 years, sea level is actually cycled up and down. So the question is it consistently, even though it's cycling up and down, is it consistently rising or not? But a section of that, while it's cycling up, that might be exponential growth. And when it's cycling down, that might be exponential decay. So there's a possibility that it would fit. Retirement accounts. That's after you retire and you're drawing them out. A lot of investment analysts or retirement advisors will suggest that you withdraw 8% a year or something like that out of your retirement accounts. That allows you to keep your balance. Your balance actually doesn't decrease that fast because you draw interest on it, but it allows you to keep a constant income while your balance only slowly decreases. Radiation is exponential decay. Okay, that's one that's usually the stereotypical one, radiation. And another one that's more applicable than people think, and you don't usually think about it, is drugs and alcohol in the body. We'll just say in the bloodstream, in the blood. Your body usually metabolizes alcohol or any medications you take at a certain percentage every hour. Okay, so let's take a look at in your packet in M5. We are looking at page, or hopefully it's page 7 of yours on M5 as well. It's problem number 3. In M5, so number 3 in M5. And we're looking at the cost of attending a 4-year college is $16,500. The cost increases by 3.2% each year. So a couple of questions. One is, what is the starting amount? Perfect, the 16,500. Growth or decay? Growth. And the rate of growth? Oh yeah, it's 3.2%, so yes, we're going to use the 103.2. So I want you guys to come up with a model to represent this balance, the cost of tuition for this college. I'll just give you, 30 seconds here and we'll talk about it. So what's the model going to look like? Perfect. So cost is the cost of tuition on a given year equals 16,500 times the 1.032, represents that 3.2% constant growth rate. T is time, and we should be specific, years after, what was the first year named in this example? 1977. I didn't expect you to specify that on this one, but I wanted to point that out, that we do have to, when we create a model, make sure we specify those. Otherwise, if T is 5, what does 5 mean? Well, 5 would be 1977 plus 5 would be 1982. So what I want you to do, we're going to look at the next question here. What would the tuition be in 1987, 1997, and 2012? So fill in those values quick. There we go. So for 1987, it's going to be the 16,500 times 1.032 to what power? 10th power. Good. So what do we get for that? Perfect. $22,608.98. For 1997, it's the same model to the power of 20. And what do we get there? Perfect. And then in 2012, same model to the power of 35. And what does that give us? Okay, perfect. So tuition is rising. If it was that much in 2012, I know I definitely can't afford to send my son there. So anyway, hopefully the tuition isn't rising at 3% anywhere around here. So anyway, what I want you to do now is I want you to ask, in what year would the tuition be $33,000? Now I asked for $33,000 for a very specific reason. What's its relationship to the original tuition? It's doubled. Very good. So I'm asking, what year would the tuition be doubled from the starting amount? Now, looking at the table here, we can narrow it down a little bit because 1997 is less than that. 2012 is definitely more than that. So we know it's somewhere in between there, probably a little bit closer to which one? 97, good. So figure out what year it doubles. I'll give you a minute. So you probably didn't get an exact value, but how did you guys approach this problem? I'm guessing probably guess and check. Did you just pick a year and try it and see if it was about 33,000? Well, for what we know right now it is, but we'll get to some better ways of doing it. But for right now, that's really all that we know how to do. So, since it was actually 1997 was pretty close, 1998 would be to the power of 21 instead of 20. What does that give us when we do it? Oops, I did something wrong. We get 31,971.10. Well, that's not quite 33,000. Do we want to try 1998 or do we want to jump up to 2000? Jump up to 2000. Okay. Notice I left a blank line there just in case I need to go back and fill that in. So this is going to be the power of 23. Good. Now I'm going to cheat because my calculator allows me to do this and just change the power. 34,049.99. So that is a little bigger than we need it. So we're going to have to go back and try 1999. What'd you come up with? and 18 cents. So we're like not quite $6 away. So that's close enough to 33,000, right? So in 1999 is where we doubled. How many years was that from 1977? 22 years. If we have a college that starts out with tuition at $4,800 and increases by 3.2% each year, I'm kind of shorthanding my writing here. How much would it be? How much would it be after 22 years? I'm going to give you a minute or two for the two of you. You can discuss it between yourselves if you want to. Figure out the formula of the model and find that balance of tuition after 22 years. So our model is going to be what? Cost of tuition equals perfect. What do you get? $0.31. Okay, we notice that is almost exactly double the $4,800. So the time to double was the same if we started with 16,500 or 4,800. So the starting amount doesn't affect the time it takes to double. What must affect the time it takes to double? What part was the same between these two problems? The rate, exactly, the 3.2%. Now I want to look at this. Let's say there are 800 milligrams of medication in a patient's blood. The medication decays at 3.2% per hour. How much is in the blood after 22 hours? What do we end up? I will give you guys a minute or so to create the model and do the calculation and get that level. What's the model going to look like for this? The amount in the blood is going to start out with 800 times perfect. That was the 100 minus the 3.2, right? Perfect. To the power of 22, and what's that give us? That's a very good question. Realistically, it depends on the application. Here, I didn't really specify. Let's go just to the nearest tenth. 391.2. Okay. You'll notice that is half of what we started with. So the time to double or the time to cut in half doesn't depend on the starting amount, doesn't depend on whether we're growing or decreasing. What it depends on is that percent. Now, we haven't talked about this next little thing at all. I was looking ahead to make sure I'm not getting too far ahead of ourselves. Next, you know what? I'll talk more about this on Wednesday about how to reverse an exponential growth model. But the big things I want to make sure we get out of today, 2 things. Types of models we've looked at. The first type of model we've looked at is linear. And just to review, why is a linear model called linear? Yeah, it's a line on the graph, right? So a linear model is named after the shape it creates on the graph. This other model we looked at is an exponential model, and it can either be growth or decay. It is named not by the shape on the graph, but it's named exponential because of the form of the algebraic equation. Because there's an exponent, an exponential in the equation itself. Hopefully at this point you are familiar with the form of both of those, and from the simple examples we've looked at that you can create the models, the equations for those types of situations in simple situations. The second thing I want to make sure that we have taken away from this is doubling time. And we'd even think of as halving time as well. If we look at the initial value, the starting amount, does that affect the time it takes for a value for it to double? When we had 16,500 compared to the 4,800, did it change the amount of time it took for that amount to double? No, it doesn't. The starting amount does not affect the time it takes to double or cut in half. What does affect it? There you go. The rate of growth, if it's doubling, or decay, if it's halving. For the doubling times, by the way, since we've got a couple minutes yet, and by the way, that doesn't affect whether it's doubling or tripling or quadrupling or whatever. It's the same thing. It's the rate of growth that affects that time. Next class, we'll look at how we could calculate that time using algebraic methods rather than just, we did trial and error here. But for doubling, there's something out there, if you look at business math and compound interest, something called the rule of 72. What that is you take 72 divided by the rate is approximately, I shouldn't use the equal, let's use approximately equal to the doubling time. So we use 3.2% here. So if I take 72 divided by 3.2, I shouldn't say rate as a percent. I should put it in there. So 72 divided by the 3.2. We don't have to put it in decimal form. Gives us 22.5. In our examples, we were finding 22 years, it was really close to double, but not quite. It was a little bit more than 22 years. It's actually a little bit less than 22.5, but you can see that's a really close approximation. So we've got 4 minutes left. I want to make sure we know what's coming up for assignments. So what'll be due, I like to have the homework due the day after class so that you have some time to ask questions and whatever in class if there's anything confusing. So what'll be due tomorrow is the out of class exercises for, let me get my calendar up here, unit 4. For M4 and the P&L for M5. Due, what'll be coming up due Thursday, you should start working on them at least for class on Wednesday. It'll make it a lot easier for us. Is I want you to look ahead at the P&L for M6 and work on the out of class exercises for M5 from what we learned today. So taking what we learned today and then preparing for what we're going to work on Wednesday. Now I realize I've been a little bit more guided than I should be today and last week as well. I am going to start pulling back a little bit and going a little bit more off of the modules in the items you have from online. I just kind of wanted to get everybody pushed up to pace, and I also tend to drift when I teach a little bit. So on Wednesday, I'm going to try to stick a little bit closer to the materials in the packet. So we'll be looking at M6 on Wednesday. You guys have any questions before we lose our connection? Okay, well, we've got about a minute and a half. If you guys want to take off, that's fine. Or if you want to take a look at some of those and see if any questions pop up, that is fine as well. We will see you on Wednesday. You bet. You guys have a great day. Thank you.